All right, so polyatomic ions. Polyatomic ions, you're going to have to draw square brackets around your entire Lewis structure, and the charge is going to be placed in the upper right-hand corner outside the brackets. That's what you see right here. You see your brackets and your charge, your brackets and your charge, okay? Your charge indicates the overall charge spread out among all the atoms in the ion. And for polyatomic ions, you have to account for the electrons gained or lost due to its charge. So, for example, on your left, you're going to add 2 electrons to your total number of valence electrons because you gained 2 electrons, okay? So you're going to have to, with the negative charge, you gain them, you're going to have to compensate for that. And the same thing goes on the right for your ammonium ion. Your ammonium ion, you're going to subtract 1 electron for the entire total amount of the valence shell electron for your positive charge. Okay, so if we go right back over to our HF, let's talk about HF again. One exception to your octet rule is hydrogen. I mentioned it just a few minutes ago in the last video. It's going to be such a small atom, it can only hold 2 electrons. So for HF, or hydrogen fluorine or fluoride, H has the 2 electrons it needs from the bonded pair it shares with fluorine. Okay, and fluorine has an octet, which is 6 non-bonding electrons that are going to be paired together, and then the bonded pair, which is the 2 electrons that the 2 electrons it's now sharing with your hydrogen. Okay, so there are more exceptions to the octet rule, and we're going to get into that in just a few minutes. But here we go. Actually, we're going to get into it right now. Some exceptions. So in some molecules and polyatomic ions, the central atom may have less or more than an octet. So your molecules with your incomplete octets, we're going to talk about beryllium and boron. So beryllium and boron can form molecules where beryllium only has 4 electrons and boron only has 6, right? So these compounds are going to be unstable, and they're often reactive pretty immediately with other atoms or compounds. So they will gain their 8 electrons, valence electrons, or octet, but they do exist for a short time in the world as having less than 8. So our next exception is going to be molecules with an odd number of electrons. So there are a few molecules that have an odd number of electrons. Now these molecules are called free radicals and very unstable and reactive. They tend to react with other free radicals to pair up their unpaired electrons. Now your molecules included in this particular experiment, what we're working on in this class, this is not for everyday real world chemistry, this is for what we're working on. Those free radicals are going to always have nitrogen as your central atom, and the nitrogen will only have 7 electrons, okay? And that is true for what we're working on in molecular modeling. So let's just see an example real quick. We have molecules with expanded octets. Now you can have molecules or polyatomic ions that have 8 valence electrons around your central atom. Your central atom can have expanded octet only if it's from period 3 or higher. So when it says only from period 3 or higher, it means to go down, because you have period 3 through period 7. Now, all of these can have an expanded octet if they are the central atom. The central atom, it's basically what happens is you have d orbitals that are going to be available to hold additional valence electrons. So if you think about it this way, we have sulfur, which is right here, right? And we have oxygen, which is right here. Now, your sulfur can have an expanded octet because it is in period 3. 1, 2, 3, just as a reminder. But our oxygen, it cannot have an expanded octet. It is in period 2. Now, it is too small to hold more than 1 octet. So if we look at this, we are actually going to draw the Lewis structure, and I'll draw it out here, CH3L. All right, so the very first thing we want to do is we want to count up our total number of valence electrons. Our carbon, if you remember by looking at your periodic table, it is in group 4, so it has 4. Our hydrogen has 1, but there are 3 of them, okay? And then our chlorine, that is going to have how many? Chlorine is in group number 7, and there's only 1 of them. So we have 4 plus 3 plus 7. What's that give us? 7, 14. All right, 14 total valence electrons. And that's what you got here. I just explained it to you typing, but I just drew it out because I like to draw when I'm trying to figure out these problems. It makes it a little easier, okay? And this is how we actually came up with our total valence electrons, okay? All right. So let's move on to the next one. Once we have the total number of valence electrons, we're going to take our total number divided by 2, and that's going to give you 7 electron pair. That's all you need to know. 7 electron pair, and you are moving on to the next step, okay? You want to remember that your central atom is the least electronegative. Your central atom is the least electronegative. Now, although hydrogen is less electronegative than carbon, hydrogen must always be an outer atom. It has to always be an outer atom because it's too small. It can't hold that octet. So I just want to remind you of something that I just reiterate to you as we're working this out. So carbon's going to be your central atom, and then your chlorine atoms and your hydrogen atoms are all going to be outer atoms, and that's what you're looking at here. You have your carbon, which is right here, and then you have your outer 1, outer 2, outer 3, and outer 4 atoms, okay? So if we go and we start connecting, we want to connect all the atoms with a single bond, right? So we have 2, 4, 6, 8. We know we have, we started needing 7 electron pair, okay? So if we needed 7 electron pair, we know we needed 14 valence electrons total. Now let's subtract our 8 that we have here. If we take those away, we used 4 bonding pairs in our single bonds. Then there are going to be 3 pairs left, which is 6 valence electrons, or 3 pair. And you can think about it any way you want, in pairs or in singles. I like to think about it in singles. You think about it, whatever works for you is going to be perfect. I'm happy with that. So once we do that, the carbon atom, which is your central atom, has an octet because we have, what do we have? We have 1, 2, 3, 4, if you're talking about pairs, okay? Or if you're talking about single, let's just do it for those who want to think about it in singles, you have 2, 4, 6, 8. So remember, we have 14 minus 8, that leaves us 6 valence electrons that are kind of, we still have to put out there. So each hydrogen atom has a pair of electrons, which is all it can handle. Remember, only 2 for your electrons for hydrogen. And then the last 3 pairs are going to be put around the chlorine atom so that it also has an octet. Now, all the atoms have an octet, so we have these, right? And we added these, so there's 2, 4, 6, and we use those, so now we're at 0, check. Okay, let me go ahead and make sure that you guys know. This is what the actual structure should look like. Not without all of the writing on it, but this is your actual structure. To finish this case, you're going to count the electrons and make sure there are in fact 14 total, which we did, and there are no more or no less in the final Lewis structure. So this is going to be your final Lewis structure. And let me just throw it up there so I can go ahead and erase all of this. Your final Lewis structure, just so you can see. Okay, that's going to be your final Lewis structure for that one. Now, I want to show you NO2. The first thing we're going to do is we're going to figure out how many valence electrons. You guys can figure that out. I've shown you how to do it. The answer to that is 18 valence electrons. So if we're going to take that, we're going to divide it by 2 for those of you who want to work in pair thought. And so now we know we need either 18 valence electrons or 9 pair of valence electrons, however you want to think about it. All right. What's your central atom going to be? Well, we know that what do we say? If we have nitrogen, we have a free radical, right? And it's always going to be a central atom. So we have NOO, and that's where we're going to go with that. That's going to be on that. Now we're going to connect the atoms with single bonds, right? Connect, connect. All right. So we're going to draw the structure to distribute the remaining 7 pair of electrons that we're looking for. We need 7 left, and this is where we're at. What has to happen for all the atoms to get an octet? The O atom has to share a lone pair of electrons with the nitrogen atom, and it's going to form a double bond. Okay, you're going to draw square brackets and show the charge on every Lewis structure that is a polyatomic ion. Your final step when drawing any Lewis structure is counting the electrons to make sure they're going to be displayed correctly. All right, so if we're going to talk about resonance structures, this is a good place to start. So in this case, the nitrite ion indicates that 2 nitrogen-oxygen bonds are going to be equal in length. So this structure can't be corrected since the single bonds are going to be longer than double bonds, sort of like a bond and a half. We can't draw a bond and a half, so we need both Lewis structures to show a nitrate ion as accurately as possible. And you're going to draw a double-headed arrow to indicate the actual structure is a combo of the first structure. So this is a actual combo of the structure that we're talking about. Now, formal charges. When we're talking formal charge, it's just a hypothetical charge an atom has in a molecule or polyatomic ion if the bonding electrons are shared equally and the lone pairs belong solely to the one single atom. So the charges are going to be hypothetical because formal charges are only for quote unquote bookkeeping purposes, and that just is used to determine a molecule's most plausible structure. There are no actual charges in molecules, just to be completely open and honest. So formal charges for atoms can be determined by following a formula. Now, this formula you're going to see in the lab handout and the worksheets, but I like using this one. This is the one that I like using. For me, it's easier. I already know all the information, your group number, your number of bonds, and your number of unshared electrons. So you can use either formula to get the correct answer. This formula is using everything you've learned up to here in the PowerPoint. Now, we know how to find the group number. We know how to find the number of bonds. And then we also know how to calculate the number of unshared electrons. So I like using this one. You use whatever is best for you. So there are guidelines for determining formal charges. I'm not going to read them to you. You have them available in your handout. You have them on here. If you need to reference them, you're welcome to. Make sure you reach out to me with any questions on that. So if we're going to talk about N2O, like again, we're going to calculate our total number of valence electrons and divide the total valence electrons by 2 to find out how many electron pairs we actually need. You're going to put your least electronegative element as your central atom. Remember what I said about nitrogen. Connect everything, right? Connect everything with single bonds and then distribute the remaining electron pairs around your outer atoms. Remembering your octet rule. Now, there are 3 different ways for nitrogen to get an octet, and all 3 ways obey the octet rule. Each of the outer atoms could share a pair, so the molecule has 2 double bonds. Now, the nitrogen outer atom could share 2 pairs to form a triple bond with the central atom. You would have to do your formal charges for each one of these, right? Because your oxygen atom could form a triple bond with the central atom. And basically, this is what we're looking at. You have 3 different ways to draw it. And to determine which one is going to be most favorable, which of these structures is most favorable, you're going to have to figure out the formal charges for each atom and each resonance structure. That's just the only way to figure it out. So using a formula we discussed, whether you're choosing the one in your lab or the one that I gave you on this PowerPoint, the formal charges are going to be determined just like this. This is how we got there. Okay. If you have questions about formal charges, make sure to check that video out in the video library. This shows the formal charges for each atom. Now, we found these charges by using the formula on each element individually. And because the higher the formal charges are less favorable, the structure with the higher charges are not likely. The more favorable Lewis structure has the negative charge on the more electronegative atom. Now, since oxygen is more electronegative than nitrogen, the -1 charge should be on the oxygen atom. The actual N2O molecule is a resonance hybrid between the first 2 that you see here, and the second is actually more favorable. Okay, so when we're talking about favorable, we want to note that